Okay, welcome back again. Today, let's continue our discussion on equations of motion, but this time we have a different type of inertial frame of reference, which is the normal tangential coordinates, also known as the path coordinates. So before anything else, let's discuss the procedure in solving these kinds of problem. So previously, we discussed about the procedure on solving the equations of motion under the inertial frame of reference, which is the rectangular coordinate system, and we had plenty of examples. What about the procedure for equations of motion under the inertial frame of reference, which is the normal tangential coordinates? So previously, we know that if the acceleration of a particle is given or known, we can use the equations of motion to find the forces, correct? And if on the other hand, the forces are given, the equations of motion can be solved for the accelerations. But most problems, however, are kind of mixed, wherein where only some of the forces are given, especially if you're dealing with 3D problems, and also some of the acceleration components are known. Okay, so the most common type of method in solving this problem is known as the FMA. We have discussed this previously. It's called the FMA. And the meaning of that is the force mass acceleration. Force mass acceleration. We try to solve the acceleration given the force, and we try to solve the force given the acceleration. Of course, mass is always given in almost any kind of problem. Other methods are also it says now, like work energy and impulse momentum methods, but our focus for this time is only on the equations of motion. Okay, so what about the procedural analysis? So basically, the procedural analysis for normal tangential coordinates and radial transverse coordinates are very much the same with rectangular coordinates, except for the kinematic part. So of course, we have the establishments of the FBD, because it's important, because all the necessary forces must be known. Okay, and then of course, after establishing the free body diagram of the particle or of the body, the next usual step is to perform kinematic analysis. Kinematic analysis. And of course, sometimes we include in the drawing the mass acceleration diagram. And the next part is of course the formulation of the equations of motion. Equation of motion, which oftentimes involves the pairing of FBD and MAD. This is the derivation of the motion. So pretty much the same with rectangular coordinates procedure, except for the, again, kinematic analysis, because our inertial frame of reference is quite different than that of rectangular coordinates. Okay, so the only significant change really is in the details of the second step, which is the kinematic analysis. All right, so that's it for the procedural analysis. Let's continue. So equations of motion, normal and tangential coordinates, aka path coordinates. So as you can see here in 3D diagram, we have three unit vectors or three direction vectors. We have UT, UN, and UB. The unit tangent vector, the unit normal. This is the unit tangent vector. This is the unit normal, or sometimes called the principal normal. Principal normal, because there are many possible axes that are tangent to tangential axis, and that one particular axis is known as the principal normal, which forms the uh, plane of motion. Plane of motion, of course, composed the normal and tangential coordinates, and this is sometimes called the principal normal. Okay, so let's continue. If we're only dealing with 2D plane, the plane that is formed by the N and T is called osculating plane, as you can see here. The N and T. It is called the osculating plane for two-dimensional motion. This plane is fixed, okay, and it is the plane of motion, meaning our object or our particle is confined in that plane. It moves on that plane if we're dealing with 2D. But in three-dimensional motion, the orientation of this osculating plane is not fixed, but it continually changes. It orients itself continually as the particle moves along the path. So for instance, we have a particle here, and then it moves along this blue path. Then this plane is also changing continually because the trajectory is not simple, meaning it has a 3D curve. So the plane itself, the osculating plane, is not fixed on the space, but it is continually changing as the particle moves along the path. So for the equations of motion of a particle in terms of cylindrical components, the equation, of course, let's start with the sum of all the forces is equals to ma, because it is the net external force that causes the acceleration. So for this type of inertial frame of reference, if we're going to decompose or resolve these forces and acceleration into tangential, normal, and binormal. By the way, this is called the binormal unit vector or binormal axis. Then we have the sum of forces along the t. Of course, we have the unit vector. Then the sum of forces along the n. We have the unit vector. And the sum of forces along the binormal, and we have the binormal unit vectors, is equals to the mass acceleration along t, the mass acceleration along n, and the mass acceleration along b. And to satisfy this equation, we know that the left side of respective axis must be equal to the right side of equation. So for this, we have ft unit vector ut is equals to m vector acceleration. So fn unit vector normal is equals to m a n, and the last is fb unit vector binormal is equals to m a b, and these are the vector notation. And for simplicity, you can use also this scalar notation, which is just in the form of sum of f along t is equals to m a t, sum of force along n is equals to m a n, and the sum of force along b is equals to m a b. Okay, so for problems which involve only 2D motion, then the equation of motions that we need are only these two. Okay, so recall that the acceleration, tangential acceleration, which is of course equals to dv dt, this type of acceleration, it represents the time rate of change in the magnitude of the velocity. Okay, it is responsible for the change of magnitude of the velocity. So if tangential force acts in the direction of motion, then it's either it either increases or decreases the object. It either slows down or increase the speed of the object. While the an, we know that an is equals to v squared over the radius of curvature. And this type of acceleration, it represents the time rate of change of the velocity's direction. The direction of the velocity. And it is caused by, of course, no other than the normal force, which is always acting on the positive n direction. The positive n direction, which is toward the center of curvature. Meaning if the path is going like this, and if this is the instantaneous center, and the object is here, then the normal force is always acting on the positive direction, which is towards the center of the curvature. And it is the reason why it is called centripetal force. Centripetal force, because it always seeks the center. It is a center-seeking force. Okay, so that's it, and I think we're now ready to solve some problems involving the path coordinates.